All right, let's now look at linear dependence and spans. First concept. If a vector v is in the span of a set of vectors S, then S union v is a linearly dependent set. Okay. Recall what linear dependence means is that you can form a non-trivial relation of linear dependence. So here's an example where I have a vector, and my vector 4 minus 610 is in the span of 419 and 122. Right? 4 minus 610 is in the span of 419 and 122. Why? Because I have a linear combination of 419 and 122 that gives me 4 minus 610. All I need to do is move this vector over to the other side and create a linear dependence relation. We saw something similar in the last video. But that's all this is saying. That something's in the span, then you're just, if you add that to your set, you're going to get a linear dependent set. Right now. So, second concept, if a set of vectors S is linearly dependent, then at least one of the vectors is in the span of the remaining vectors. All right. So here I have 3 vectors, and I think it works out that they are linearly dependent. You can check. Let me just take care of this here. It should be 23. Okay, let's just make it neat so it looks nice. This is going to be 23. Work it out and make sure this is true. So they are linearly dependent. Now, how could I write one of these so that it shows that it's in the span of the other ones? Well, let's choose this one in the middle. I could choose any of them, in fact, but let me choose this one in the middle. I can take this linear dependence relation and move this term to the other side. That's what I've done here. 2 times 113, that's the same. This minus 8 times 465, I simply move to the other side of the equation. When I add that to the 0, 0, 0 that's already there, I simply get 8 times 465. Now forget about the red 8s for a moment. Just look at the blue writing. And this 2 times 15, 23, 17, that's the same as this. So forgetting about the red writing, all I did is move this second vector to the other side. Now, if I want to get a linear dependence relation, I want a coefficient of 1 on this vector. So I just go ahead and divide all the coefficients by 8. And if I do that, I end up with a linear combination of 113 and 15, 23, 17 equal to 465. So 465 is in the span of these other two vectors. Right? So you can see the strategy. All I did was take the linear dependence, move one vector to the other side, divide out by the coefficient, and then I get a linear a span relation. I get that vector in the span of the other vectors. All right, let's go to the next concept. If the null space of a matrix is non-trivial, then the columns are linearly dependent, and at least one column can be written as a linear combination of the other columns. All right, here's an example. You know that the null space is a set of solutions of the homogeneous system. All right, so here's a set of columns, and the null space will be a set of coefficients x1, x2, x3, and x4 such that these equations hold. All I did was write out the equations represented by this matrix. Right? Now that means that I can write the system of equations in vector form. X1 times the first column plus x2 times the second column plus x3 times the third column plus x4 times the fourth column is equal to 0. And just transform this system of equations into a vector equation. Now, this gives a linear dependence relation for the columns. That means that at least one of these vectors has a non-zero coefficient. I can take that vector to the other side, divide by the coefficient, and get that vector in the span of the others. So the way I said it here, What I said here was that any non-trivial element of the null space gives me a non-trivial relation of linear dependence. Now, if the number of vectors is bigger than the length of the vector, we know that there's going to be a non-trivial element of the null space. How do we know? It's our n and r business again. N is the number of variables, in this case 4. R is the number of pivot columns. Can't have more pivot columns than there are rows in the matrix. So in this case, n is greater than r. We know that there's a non-trivial there's a non-trivial solution of the null space, which means there is a non-trivial linear combination of vectors that gives 0. And as I said, once you get that non-trivial linear combination of vectors, then you can get one of the vectors in the span of the other vectors. Hang on, it's not going down. Let me just trick it for a second. All right, so as I said here, the number of vectors bigger than the length of the vectors, then they're always linearly dependent. And what I didn't write here is you can get one vector in the span of others, using the trick I showed in the last slide. All right, let's move on to the next slide. So here's concept 4. If a set of vectors is linearly dependent, then a smaller set of vectors can be found which has the same span. This is what he calls casting out vectors. All right, so let's follow this example. This is one particular example, but it really works the same way in general. Here I have 3 vectors, and I've chosen them so that they are linearly dependent. 1, 4, 5, 2, and 16, 1. Now, let xy be in the span of these 3 vectors. That means that xy equals a times 1, 4, put an equal there, plus b times 5, 2, plus c times 16, 1. All right, xy equals a times 1, 4, plus b times 5, 2, plus c times 16, 1. But I can express this 16, 1 as a linear combination of 1, 4, and 5, 2. Why? Because 16, 1 is in the span. I used my same trick of pulling the 16, 1 to the right-hand side and then dividing by the coefficient. See, that's exactly what I did here. I took this linear dependence relation, pulled the 16, 1 term to the right-hand side, and divided by the coefficient, which is minus 2. And that gives me 16, 1 in the span of 1, 4, and 5, 2. Then I go ahead and replace the 16, 1 here with the expression in terms of 1, 4, and 5, 2. So let's go ahead and do that. All right, 16, 1 equals minus 3 halves 1 fourth plus 7 halves 5, 2. I've replaced that into this here, and I get xy equals a times 1 fourth, 1, 4, plus b times 5, 2, plus c times this stuff. And then I can just redistribute this so that this 1, 4 goes with this 1, 4, and this 5, 2 goes with this 5, 2. Right? This is actually c times minus 3 halves times 1, 4. I can group that together with a times 1, 4. And that gives me, over here, a minus 3 halves c times 1, 4. Now this here gives me c times 7 halves times 5, 2. I can group the 7 halves c with the b, and I get b plus 7 halves c times 5, 2. So I get xy as a linear combination of 1, 4, and 5, 2. All right. So that means that any vector that's in the span of these 3 vectors, 1, 6, 5, 2, and 16, 1, is also in the span of these 2 vectors. And you can see you could do this in general. If you've got linear dependent vectors, you can always express one in terms of the other ones. And then in any linear combination expression, I can replace that vector with its linear combination expression. So in general, if v1 through vn are linearly dependent vectors, then it's possible to find some vector in this list. Here, let's just go ahead and put arrows here just to emphasize that these are vectors. It's possible to find some vj in this list such that all of these vectors except for vj has the same span. It's always possible to remove one vector if they're linearly dependent. Geometrically, you can understand what this means. Suppose you have 3 vectors in R2, where R2 is the plane. Okay? So here's my 3 vectors. red, blue, and black. Now, this black is a linear combination of the red and the blue. You can see I've kind of made my parallelogram here. I've scaled up the red, and then this is parallel to the blue. Since black is in the span of blue and red, then the span of black, blue, and red is the same as the span of blue and red. In other words, the black doesn't add anything to the span. Any vector I can obtain by a combination of these three, I could also obtain by a combination of these two. Black doesn't give me any more range to my span. Okay? Okay. So linear dependence in spans competency 1. Given a matrix, find a linear independent set of vectors that span the column space of the matrix by first taking the REF, second taking the columns of the original matrix, which correspond to the pivot columns in the REF. Now here's an example. I just chose this matrix out of the hat, and I took the REF, and this is the result. Now, what does that mean? That means that if I want to get a linear dependence relation, I can choose my coefficients x, y, z, w according to the specification we find in this REF. This first equation tells me that x plus 19/20 w is equal to 0. So I can rewrite that as x equals minus 19/20 w. Second equation tells me y minus 7/40 w is equal to 0. So that gives me y equals 7/40 w. Similarly, last one gives me z equals minus 1/8 w. Now I can choose w equal minus 1. The reason for that choice you'll see later, and that's the choice that we're always going to make. And in this case, we have, since this is a solution to the null space, we have x times the first column plus y times the second column plus z times the third column plus w times the fourth column is equal to 0, 0, 0. Now remember, I chose w equal to minus 1. So that gives me minus 1 here. I can pull that over to the other side and get a plus 1. So that tells me that x times 349 plus y times 261 plus z times 42w is equal to minus w times 339. With w equal minus 1, I have a 1 here, and that's going to give me 339 as a linear combination of the other columns. Now, these columns were which columns? These columns were the pivot columns. And this 339 column was the free variable column. And you'll find that no matter how many free variable columns, you can always do this. You can always express the column that ends up being a free variable column as a linear combination of the columns that correspond to pivot columns. Now notice carefully, I'm not working with the columns in the REF. The columns in the REF indicate which columns in the original matrix are the independent ones and which columns are the free variable ones. Okay? So you look at the REF, you identify the pivot columns, go back to your original matrix, and then the free variable columns in the original matrix will be a linear combinations of the pivot columns in the original matrix. So in this case, I do get this linear combination, this 1920 minus 740, 740 and 1/8. That comes from setting w equal to minus 1 in this system. So we can use this method to express any column with a free variable in terms of columns with basic variables. Okay. So here's another example that I just cooked up. Here I have a matrix, and I just gave you the row reduced form, 1, 1, 0, 7, 2, 3, 6, 2, 6, 2, 9. Now in this case, if you want to get x, y, and z, x is equal to minus 7u minus 6v, y is equal to minus 2u minus 2v, z is equal to minus 3u minus 3v. If you follow what I just said here, that xyz is minus u times this column plus minus v times this column. You can think of it in terms of columns. Now, if I let u equal minus 1 and v equal 0, that's going to give me xyz equals 722. And in this case, that tells me that 7 times the first column plus 2 times the second column plus 3 times the third column is equal to the free variable column. Now, in this case, I didn't show you the original matrix, but if I'd had the original matrix, instead of using these reduced matrix columns, I could use the columns of the original matrix. Now, I can also set u equals 0, v equal minus 1. And that would give me xyz is equal to this column here. And that tells me that 6 times the first column plus 2 times the second column plus 9 times the third column will be equal to the second free variable column. So this way I've expressed all free variable columns as linear combinations of basic variable columns. So all free variable columns lie in the span of basic variable columns. Right. There are also several examples in the book that show how to do this. All right. So use the above technique to find a smaller spanning set for an arbitrary set of column vectors by putting the column vectors into a matrix. So let me do another example here. Here I've got a bunch of column vectors. I chose myself an easy case where all the column vectors are in R2. Now I want to find a set of columns such that I can express all columns as linear combinations of those columns. That's what a spanning set is. It's a set of vectors that the linear combination gives all of the vectors in the set. All right. So here I've got my 5 vectors, and I want to reduce it down to a smaller number of vectors that span all these 5 vectors. So let me go ahead and take the REF. I did this using my Python. And here we've got 2 basic columns and 3 free variable columns. Now, the free variable columns are in the span of the basic columns. So that means that these 3 columns here, this one, and this one, are in the span of the 2 basic variable columns, which are 1, 4, and 2, 9. So that's what I said down here. 3, 7, 4, 6, and 3, 2, those are the last 3 columns here, are in the span of the first 2 columns. Now, how could you express those as linear combinations? Well, you could use the same technique that I said before. If I call this x, let's just do it quickly. Suppose we have x, y, z. So I'll say my variables are x, y, z, u, v. Okay. Now, so these are my 3 free variables. So I'll choose them in turn, z equal minus 1, u equals v equals 0. That's my first choice. Second choice will be u equals minus 1, z equal v equals 0. Last choice, v equal minus 1, z equal u equals 0. So I'll call this choice A, this choice B, and this choice C. Now let's follow up with choice A. If I take choice A, what do I get? That means that's going to give me that x. Now remember, my u and v are 0, so it's going to be x, and my z is minus 1. It's going to give me that x is equal to minus 13z, or x equals 13. And y is going to be equal to minus 5. That comes from this one. Okay, so I'm going to get, from this one, I'm going to get x is equal to 13, y equal minus 5. From this one here, u equal minus 1, z equal v equals 0, I'm going to get a 0 here. The minus 1 here, remember, it goes to the other side. I'm going to get x is equal to 24, and y is equal to minus 10. This last one, if I set v equal minus 1, z equal u equals 0, this one zeroes out, this one zeroes out, I get my x equals 23, and my y equals, again, equal minus 10. So what does that tell me? The first one tells me that 13 times the first column plus minus 5 times the second column is equal to the third column. Right? First column was 1, 4. Second column was 2, 9. 1, 4, 2, 9. Again, I'm reading off the original matrix here. The original matrix before row reduction. First column was 1, 4. Second column was 2, 9. Third column is 3, 7. So let's put that down here. Third column is 3, 7. And you can verify that, in fact, this is true. 13 times this column plus minus 5 times this column is 3, 7. So that means the third column is a linear combination of columns 1 and 2. All right, now how about the next one? The next one says x equal 24, y equal minus 10, u equal minus 1. U equal minus 1 is the fourth column. So the next one is going to give me, so this is from A. From B, I'm going to get 24 times 1, 4, plus minus 10 times 2, 9. And this should give me the fourth column, which was, go back up and see it. The fourth column, original fourth column was 4, 6. 4, 6. Okay, so let's see if that works. Okay. You can verify that, in fact, this is true. So this is the fourth column. So this should be a linear combination. I don't know why it worked out. The fourth column is a linear combination of 1 and 2. Okay, then we can do part C. Part C was 23 and minus 10. Part C says 23 times 1, 4 plus minus 10 times 2, 9. And that should be equal to the last column. Last column was 3, 2. I'm looking up here at the last column, 3, 2. Remember, we're looking at the original columns of the original matrix, so this is equal to 3, 2. And you can verify that this also works. So this is the fifth column. Okay, so to recap, the very important principle here is that the free variable columns of your original matrix are all linear combinations of the basic variable columns of your original matrix. You need to row reduce to identify the basic columns and the free variable columns. Once you've done that, then you can express the free variable columns as linear combinations of the basic variable columns. Okay.